How's your weekend?
It's good.
Good. Yeah. Anything fun? No.
Nope, just lounging around.
Okay. Yeah.
So that was nice.
No, that's good relaxation. Yeah.
Yeah.
That's great. Do you proctor the exams themselves? Like this
Yeah, I
semester?
write the
Gotcha.
exams, yeah.
You write the exams and then you proctor for the exams? Okay, got it.
Yeah.
Wonderful. Yeah. Because I took this class online.
Took quarter one online.
Yeah, because they like it was pandemic time. That's why, yeah. So I had Baldwin and I took OChem 1 here, like online. And I took OChem 2 with Dr. Paul. Love him.
Yeah.
But yeah.
Good morning, everyone. How you all doing? Good? All right, we have a guest announcement.
Hi.
Go ahead.
Hi, everybody. Can everybody in the back hear me real quick? Great. Okay, perfect. So, first of all, my name's Prasenjit Sahu, and I'm a learning coach. And I was like sitting where you are as a pre-med student, and I still am a pre-med student, like a couple of years ago, right? And I just graduated. So, what happens is I want to provide you with a tool called Yinsight. And I'm the founder of Yinsight. And what we're trying to do is help you guys learn like that, like very fast learning. So if we take a quick poll, raise your hand if you guys struggle with any of these issues, okay? How many of you struggle with procrastination? Okay, you want to take a quick peek around? All right, keep your hands up. Who struggles with mental health or having a good mindset, healthy mindset? Great, keep it up, keep it up. How about focus? Right? Recalling information, especially for your exam on Wednesday. All right, and time management, right? So if you look around you guys, you're not alone. Everyone has those issues, right? The thing is, what happens with your learning, right? You guys have access to all these resources. You have Dr. Walters, right? You have YouTube, you have Khan Academy for those who use it. You have, there was that one YouTuber called Organic Chemistry Tutor, right? All those people. Yet, when you come into the class, you'll have people who ace the exam, yet everyone else will get B's, C's, D's, and F's, right? So what's the difference? It's the way you process your learning, right? So what we want to do is we want to help you with that. We want to walk with you through your learning journey. So when it comes to learning, students have three stages. The first stage is they start using tips and tricks, right? So they're like, oh, let me use this mnemonic, right? Never eat soggy waffles, right? To remember north, east, southwest, right? And then what happens is they slowly get older and older, and then they start realizing, oh, I need a learning system. For these types of classes, I can study like this. For these types of classes, I can study like this, right? So math and science is going to be different than history and philosophy, right? So then what happens is a lot of people actually get stuck at this stage, right? But what really needs to go on is we need to make a productive lifestyle change, right? If you stay up till like 1 a.m., do you think you're going to be really ready for a 9-10 class? No, right? So what needs to happen is you need to be able to take the learning, the system and everything, put in some productivity to make a learning lifestyle. And that's what Yinsight's doing. What we do is we have 4 stages, all right? 2 of those stages is going to build your peak mind and peak body. So see your vision and set the structure. So you're planning out your day in 5 minutes or less, and then you're building a growth mindset, literally helping you with all the issues you just rose your hand for. And on the other side is sync and seal. This directly affects your learning because sync is all about building that focus and building it with your friends, right? You guys have an exam this week. Who is more focused? Who can score higher? That's the goal. And then with seal the deal, we're retaining, recalling, and applying information wherever necessary. Cool? So when we bring all 4 of these things together, we get Yinsight, right? And so this is like a quick teaser of what the app is about. And we're having a beta launch, and we'd love to get you guys on the wait list. So if you guys have a chance, please go ahead and scan the QR code, and that way you guys will be on the beta list. Perfect. Perfect. Thank you guys so much, and thank you, Dr. Walters, for helping your students not through just OChem, but also through just lifestyle learning. All right, that's it. Thank you.
See it? Oh, is that one yours? Okay, good. All right, does anyone have any questions before we get started? Okay, cool. So, I'm really glad, oh, he already left. I was gonna say, I'm really glad that he was able to come in and do his sales pitch because his like teaching philosophy aligns with mine, where it's like you are a person and so you have to kind of meet the person where they're at in order to make sure that they can learn. So I just thought it was really cool that he's trying to develop an app that can help support you through kind of the extra parts of your life to make sure that you are being most productive in your student part of your life. So I just thought that was kind of cool. So hopefully it'll be beneficial to you if you want to try out the beta version. If not, well, hopefully then you'll talk to people and maybe you'll want to do it and it'll become a real thing. All right, so where we left off last time was looking at our synthesis problem, and we had stopped where we were trying our different initial steps. So that's where we ended, was like, okay, we knew we needed these bond connections, and we were trying to figure out which one, what order do we do them in, right? So it was, we couldn't do this one first because it was mismatched because you had two electrophiles, so that was no reaction. You need the paired reactivity. Then we said, all right, if I do my methyl Grignard first, I get the oxygen on the wrong side, where I was just trying to mimic where I ultimately want it to end, right? So I wanted that methyl adding to the same side where the oxygen is located. So that was not what I wanted to do first. And so then I looked at, okay, well, if I do the cyclopentyl first, that builds the correct like bond connection that we needed, where we needed the oxygen on the left, the cyclopentyl on the right. So we were like, all right, that's probably what we're gonna do first because that was the correct regioselectivity, right? That was the right connectivity. All right, so then through the rest of this, hopefully you tried it on your own to finish the rest of the problem. If you didn't, hopefully you at least looked at the notes. If you didn't, well, we're gonna go over it now. So, so the next thing that we wanna do was, all right, we did our Grignard addition. Remember that the Grignard is a strong base, so it doesn't end with the OH. In order to get the protonated alcohol, you must do the acid workup. So that is paired up to go from the O- to the OH. So when you're in your alcohol, it's like, all right, cool. Then I can either do step A or B, right? Those are my other two steps. I did step C, was the cyclopentyl addition. All right, well, if I just am like, all right, cool, let me just try doing A first. Well, that will work. I have a nucleophile of the alcohol, the electrophile of the iodomethane. That's paired reactivity, so that'll create my ether. So that even is creating the correct bond connection that I want. That puts the methyl where I want it. So at the moment, that's looking really good. But when I go to add my methyl magnesium bromide, I get SN2, where now this really strong nucleophile is going to be able to, I mean, there's no good leaving group, but the best leaving group would be the methoxy out of the non-leaving groups that I have. So that would put the methyl on, but kick out the OME, because that would just do straight SN2, right? If I just use that Grignard as a nucleophile with no carbonyl, then it just does SN2. So that is not what I want because now I've lost my ether and I needed that oxygen. And furthermore, I'm now left with an alkane. So trying to add a functional group onto an alkane is very, very hard. So that kind of left us stuck, really, with nothing else to do with what we know at the moment. So then we're like, all right, well, cool. If doing A first didn't work, let's just try doing B first. Well, remember that your Grignard isn't just a strong nucleophile. It's also a strong base. For just the same reason that you needed an acid workup, if you add the strong base, all it's going to do is deprotonate. All it's going to do is acid base because I have an acidic proton. The oxygen is very electronegative, so when it's attached to the hydrogen, you get that dipole. So it's a delta positive hydrogen. That's an acidic proton. I can't have acidic protons around with my Grignard because all I do is acid base, right? That's why I couldn't have an alcoholic solvent either. That's why I need an aprotic. So at this point, you're probably thinking, well, shoot, now we're stuck. Now what am I gonna do? Like the different bond connections we thought of, we just tried all of them and we got stuck. There wasn't anything that we could do. So we need to now think of alternatives. So we must be missing a step. The other thing that can help us is that when we did this, we did our Grignard and then our acid workup. There are 3 steps here, but we only had 2 additional reagents that we were looking at. So that's saying that maybe there's something else that we need to do first, right? We must be missing a step. So hopefully you would then consider, I need an electrophile to add that Grignard in, right? So the question becomes, what are the other electrophiles that we've added Grignards to? And hopefully from your reaction notebook, you would remember, or your reaction roadmap, or whatever you're using to get organized, you would have remembered we used it with carbonyls, right? With our aldehydes and our ketones in order to make our alcohols. So if I need that alcohol to become a carbonyl, the question then becomes, all right, cool, how do I do that? Well, I'm increasing the number of bonds to oxygen, so I'm doing an oxidation, so I need an oxidant. So then the oxidants that you want to pick would be either PCC, so the chromium oxide with hydrochloric acid and pyridine, or the Jones reagent, which was the chromium oxide with sulfuric acid and water. And you do need to know those combinations of reagents. So you need to know both the abbreviations and what combination makes them. So both of them would be correct combinations. Both of them will turn my secondary alcohol into a ketone. That both works. Why don't I want to use potassium permanganate? Yeah, potassium permanganate is that super strong oxidant. It turns everything into carboxylic acids. So it would do oxidative cleavage. It would break the bond and be like, you're now an OH. We don't want to get up to a carboxylic acid. We don't want to lose any of the carbon bonds that we've already worked so hard to either add or maintain. So we don't want to do potassium permanganate, but we could do either PCC or Jones, whichever one you want. So now I have an electrophile. So now I can add in my methyl Grignard to get to that O-. That adds in the methyl exactly where I want it to be. So you may have instinctually wanted to protonate this because we usually do acid workups right after the Grignards. The reason that we don't here is because I restricted the number of steps that you can do. So right now we did Grignard, acid workup, oxidation, and then we added our addition or our Grignard to do that additional addition reaction. So we're right here. You get 1 step to build out this last bond. So if you do an acid workup, you've now run out of steps and you haven't made the necessary product. Fortunately, we're okay with that because instead of doing the acid workup, I can just add my electrophile, right? I can do that Williamson ether synthesis, right? Because this is an ether. And for the Williamson ether synthesis, you just needed alkoxide, O minus, and a good electrophile to just do an SN2 reaction, right? So without even needing my acid workup, I can just go, sweet, you know what? You just are a good nucleophile at the moment. Let me use you as a good nucleophile and get that last carbon bond connection that I need to get that last oxygen methyl bond, right? So hopefully that's kind of the thought process you would have gone through to recognize what the order of steps that you needed. Does anyone have any questions about that? Yeah. Mm-hmm. Yeah. Yeah, so I'm so glad you brought that up. So is that a chiral carbon? No. So the wedges and dashes here don't actually mean anything. So I'm hoping where your question was going is the fact that this is sp2, so why did it only add as a wedge? And the answer is it wouldn't. It would add as both the wedge and the dash. Just like every time you add to an sp2 carbon, you get that front and the back. But here, it doesn't actually matter. Because here, it is the same. They're both methyls. Was that your question? Sorry, I kind of cut you off. Mm-hmm. Oh yeah, if you just did straight lines, that would still be 100% correct. This is a chiral center. That one must stay there. You need that wedge still there. But the left side, if you just did straight lines, that'd be 100% correct. Yeah, I just retained the wedges and the dashes because that's what was given in our original question, was it had the wedge and the dash. So I was just trying to keep my molecule looking like it, but you could absolutely switch it to lines because it's not a chiral center. Okay. Any other questions? Okay. Does that thought process make sense? Identify what you have and what you want. Try to find everything that's different. Find those key bond disconnections. Think, how do I know how to make that? That's where the reaction roadmaps come in clutch, where you got to make sure that you know, how do I make these things? What are the reagents that I know how to make these things? So we need to know those reagents. When in doubt, if you can't remember, use your synthons. So remember that, all right, well, what's the inherent reactivity of if I just have this bond and I need to break it, which one's more likely to be a nucleophile or an electrophile, right? And you do that process to then think, okay, what's a nucleophilic source of carbon? Grignard. What's an electrophilic source of carbon? Just add on whatever's your favorite leaving group, right? Anytime you need carbon as an electrophile, just add a leaving group. Now it's an electrophilic carbon. And then try to predict the order of the steps. And if this, usually this, I call it empty box syndrome, where most students see this and their brain shuts down because they just go into like a panic trying to fill in all the empty spaces that they have. So then my recommendation is don't look at it. Just treat it like a normal synthesis problem. And then once you've done this work, then fill it in up here. It takes longer, but if it gets you to the right answer, it's worth it, right? So if you can take shortcuts, that's better because that saves you time. But if you're stuck and this freaks you out, then just take this part, your starting material, your product, write it on scrap paper, and just do your normal process, just like what we did for all of these questions in lecture. All right? Any questions about synthesis? Okay. Do we want to do this hard mechanism question? Yeah? Okay. So let's practice our mechanisms, because I can guarantee you, so for every exam, I always have some sort of like multiple choice or multiple answer. Then I have that open-ended, which is more like the concept based. Do you understand conceptually what's going on? And then, so it's like you would write in words to explain, well, this is the better nucleophile, or this is the better leaving group, or because of sterics, that, or the 3 factors that stabilize your carbocations, that having your induction, hybridization, induction, hyperconjugation, and resonance. Like those sorts of conceptual questions are, you're trying to explain the why. Then I will have a predict the product, which is going to be where you're filling in the structures, and then there will be some sort of mechanism question. So that'll be the format where you're gonna get all of those. So when we look at our mechanism question, for this, it helps to map onto the product again. So this is, I know where I need to get, so I need to identify what are the key bonds that are being formed. So what I look for is some form of similarity. I still do that, what's the same and what's different, but the difference here is you will not add any new reagents. This is everything you have. You cannot add any new reagents. So unlike synthesis, where you can create whatever reagents make it work, here you got to figure out the arrows to explain how those reagents did this, right? That's what you're trying to fill in. So you want to now think, all right, what do each of these things mean? So starting out, I'm going to see like, all right, what's different? I recognize that I need to lose the alcohol, right? I need to lose that. I have to gain a thioether. That's new. I have to go from a 4-membered ring to a 5-membered ring. And whenever you see that, the change in ring size, either going from small to large or large to small, that's going to be usually a rearrangement, is going to be what's helping you there. So if we're doing rearrangements, that immediately tells you which mechanism does this have to go through. SN1. I knew it was substitution because I don't see a double bond in the end. That's what told me S. Then the fact that I have rearrangements, that's what told me SN1, right? That's how I know that's the mechanism that we're going to have to go through. So then that's ultimately the mechanism that we're going to do. It's going to look more complicated because it's going to have a rearrangement that we're doing a ring expansion, but that's ultimately what we're trying to do. So the next thing that I recommend that you do is identify your carbons. Try to match on whatever carbons you have to see which carbons need to change. So the easiest thing to do is find an anchor. So what I see in my product is this methyl, carbon, methyl. I see 2 methyls on the same carbon. When I look on the starting material, I'm going to try to find the same thing. And I see methyl, carbon, methyl. So that tells me that not necessarily, but it could be that this carbon is this carbon. And I'm going to hope that that's the case to make my life a little bit easier. So I'm going to try to make that connection. So that means that I'm going to ultimately need to have this be, so if this is 1, 2, 3, 4, 5, then this is going to be 1, 2, 3, 4, 5. So I need to make a connection between 5 and 1 and break a connection between 2 and 5. Right? So those are all the changes that we need to do. So if you can think of what do I need to do, it can make it a little bit easier to think of how do I do that. But worst case scenario, trust that like if you have a strong acid, protonate something. Then try to always get to potentially the most stable carbocation, recognizing that you got to get to this product. All right, so has anyone actually attempted this problem yet? A couple people? Most people haven't. Okay, I'm gonna give you like 2 minutes because I don't want to spend a lot of time on this. I'd like to get through, the general review session. But go ahead and try it. Knowing that information, now that we've set it up, see if you can try to actually make those necessary bond connections. All right. So you may not have finished. That's fine. That was a very short period of time. But just for the sake of, trying to keep the class moving along, we're going to go over it together. So what do we need to do first? Yeah? Yeah, we have a strong acid. So we need to protonate something. The alcohol is our most basic site. So we're going to protonate it. If you wanted to use the solvent to create it wouldn't be an oxonium, a thionium? I don't know what it's called when it's sulfur. But if you wanted to use solvent first to deprotonate the sulfuric acid, fine, but you need to show that. So that would be an extra step you'd have to draw in. So if you want to be lazy like me, I'm cool with that. You can just start with sulfuric acid. The way that I do the abbreviation is that I just show the necessary bond that I need, but make sure that when you're expanding it out, that you are indicating that that hydrogen is attached to the oxygen, which is attached to the sulfur, right? You need to make sure that you're showing the necessary bonds. So if doing this looks weird, then just draw the whole thing out. Just draw out normal sulfuric acid. But you need to show the disconnection because we're showing the curved arrows. So you need to show the full thing. So we're gonna start from our alcohol. We're gonna have that lone pair drawn in because we're starting where we have the concentration of electron density. So we start at the lone pair. We go from the lone pair to the hydrogen. Hydrogen can only make one bond. So then we break the hydrogen-oxygen bond and give the electrons to the oxygen, right? So those are the curved arrows for that first step. And then we put equilibrium arrows because this is an acid-base reaction. And for every acid-base reaction, I want you to make sure you remember that they are highly reversible. All right, so then we redraw everything that was not a part of the arrows exactly the same as it was. And if you want to switch to line diagrams instead of showing each of these carbons written out, also perfectly acceptable. I will switch over to that probably on the next step. Also, you can either write plus that HSO4 minus, or you could show it as that oxygen with the negative charge, or you could write minus HSO4 minus over the arrow, right? All three of these are equivalent. So either write minus over the arrow or plus that to indicate that you recognize that that's the inorganic byproduct. So in my instructions, I will tell you to make sure that you show every organic and inorganic byproduct. That means write everything. Write every counter ion, write every formal charge. You got to write every single thing out because that's the point of the mechanism question, is I want to make sure you know exactly what's going on with all of the elements in the problem. All right, so right now we protonated it. Now what? What's up? Yeah, have the leaving group leave, right? Remember that if we know it's SN1, we just made a good leaving group, and then the first step of SN1 is leaving group leaves. So yeah, we're gonna kick that out. So our next arrow is simply loss of the water. And again, you can keep maintaining equilibrium arrows, but because this is an acid base, I'm okay if you just do a forward, right? If you want to do equilibrium, that is technically more correct, and so that's absolutely fine. The only one that would be graded would be this first one. That's the one that would get graded. And then you either write minus H2O or plus H2O, because that's an inorganic byproduct, so you need to acknowledge that it went somewhere. All right, now what? We got our carbocation. Rearrangements, yes, now we're gonna do a rearrangement. All right, where's our rearrangement? Let me put some numbers in again so we can indicate it. So I'll maintain the same numbers that I did from before. So I made that 1, 2, 3, 4, 5. So what sort of rearrangement are we doing? Yeah. So if I do a hydride shift, then I'm gonna have, if this moves over, I gotta move my plus sign out of the way, sorry. If that, there we go, goes to the carbon, not to the bond. So if I get that hydride shift, that does lead me to another tertiary carbocation. So I can appreciate that mentality of I'm trying to keep stable carbocations, but here we're gonna see, well, if I get that tertiary carbocation, I don't really have any way to break the ring, right? I need to break the ring, which ultimately, that's the driving force. So hopefully in your mind, while you're drawing these arrows, you're thinking, why am I doing this? I was told to not do carbocation rearrangements unless it led to something more stable. We were always talking about the carbocation stability before. Certain things can overcome or they can be more important than just the carbocation stability, which having that release of ring strain, that's our driving force. That's what we're getting to more stable. So the carbocations becoming either secondary or whatever is not going to be as big of a factor because the biggest benefit is having release of the ring strain. Also, I got to make this thing. So I just got to find some way to do that. So I love that you were thinking hydride shift, but hydride shift takes us here, and I don't know about you, but I don't really know what else to do from here. Like I get stuck. So then I'm gonna say, okay, to be honest, when I did this problem myself, I did the same thing. I did exactly that. I made this thing, and then I went, I don't know what to do now. So then I was like, okay, well maybe I'm not doing a hydride shift. Maybe I'll do the other one. What's the other one? Alkyl shift. So instead of it being that hydrogen, instead of doing hydride shift, So doing the hydride shift led to the tertiary carbocation, but not the bond connections that we needed. So we got stuck. So instead of doing that, we're going to try an alkyl shift. So what alkyl group do we want to move? Carbon 5. So remember, we wanted to break that carbon 2, carbon 5 bond. We want to break this line. I know it looks weird because it's in a ring, but if you just like imagine like that ring part isn't there, then it's just the same as, oh, there's just an R group that can move over, right? So like if I erase, I'm going to temporarily erase, but I'll bring it back. If I erase those, then it's a little easier to be like, oh yeah, the carbon can shift over. Hopefully you see how when we had like a methyl or whatever, it did the exact same thing, right? It's just that now it's in a ring, so that just means the other bonds will just come along for the ride. So we're gonna start at the carbon 2, carbon 5 bond, and then point to the carbon 1 atom. So that way we are showing that we are expanding that ring. And numbering your atoms is always really helpful to make sure that you're doing the correct, especially with rearrangements, to make sure you're maintaining the correct connections. So when I do this, I recognize that this is going to make a 5-membered ring. So I'm going to just draw a 5-membered ring, and then I'm going to go ahead and number these again to keep track of where the connections are. So off of 1 is where I had my 2 methyls. So I'm like, all right, dope. I'm going to put the 2 methyls in on 1. 5 is what moved over. 5 brought the electrons with it when it made that new bond. So the one that's left naked, the one that's left wanting, the one left without an extra bond, is carbon 2. When in doubt, if you get to this point and you're like, I don't know where to put the formal charge, I don't know. Count your bonds, right? So on carbon 2, we just have 1 hydrogen. Carbon 5 has 2. When I look here, the hydrogens didn't move, so I still maintain the same number of hydrogens. Neutral carbon makes 4 bonds. Carbon 5 has 4 bonds. Carbon 2 has 3 bonds. So carbon 2 gets the positive charge. So now what? Sulfur attacks. Now nucleophile attacks. So it truly is just the same normal SM1. Looks really weird, but it's still, we did, all right, activate the leaving group leaves, carbocation rearrangement, nucleophile attack. It still is the same steps that we did for SN1. It just looks weird because we have a rearrangement. It's a different structure, but it's the same thing you've already learned, right? It's still all the same steps. So now we can bring in that thiol. Again, we're going to start at the nucleophilic atoms, electrons. So we have to draw in that lone pair. We go from the sulfur to our electrophilic carbon, the carbocation. And hopefully you're wondering, all right, well, why didn't we do another rearrangement to get it tertiary first? Like, why did we stay at the secondary? And the answer is because that's what the product told me. So at a certain point, it's one of those, you got to make what you're told to make. So you might be asked to make a minor product, right? This might not even be the major product. You might be making a minor product. The question is, what arrows rationalize this formation? So I need the sulfur on carbon 2, so I'm going to have the sulfur attack carbon 2, right? So that's why I didn't do any additional rearrangements, is because I got to make that thing. So I get my 5-membered ring back in. Carbon 1 is the one that has the 2 methyls. I now get my sulfur. Everything came along for the ride with the sulfur, right? So that sulfur now has that positive charge. So am I done yet? No, because that isn't the exact product you were given. The exact product you were given had a neutral sulfur. So what do I have to do last? Deprotonate, right? Whenever you want it to get neutral, get rid of the hydrogen. All right, so if I'm gonna do that deprotonation, what am I going to use? Remember, these are everything you have in solution. So what are we gonna use? Yeah. Say it again. So that hydrogen sulfate, that HSO4 minus, why did you pick that one? I love that you saw negative charge and thought strong base. That is like, that gut reaction I do really love and want, but we gotta remember these are one of those exceptions. Remember that if it's the strong acid, that means that it is a very weak conjugate base. We're gonna have, so if there was nothing else in solution, then yeah, we would use what we got. But that is going to be a very bad base. So we want to try to look and be like, all right, is there anything else I could use that might be a better base? Yeah, that water, I love it. Yeah, so if you would use the thiol, technically it would be okay because it is solvent, so usually solvent gets like a little pass, like because there's so many of them that like you would be like, all right, well, likelihood is that it would probably be the closest thing. But the best base in solution is the water. So if you're trying to use the best base, you want the more electronegative atom. Or sorry, well, actually you want the less electronegative atom, but you want the smaller atom because they're in the same column, not the same row. So I chose the wrong factor at first. So remember, when we're talking column, it's size that's more important, not electronegativity. Row is electronegativity, column is size. So when they're in the same column, I want the smaller atom. The smaller atom is oxygen. That's why oxygen is the better base. So I'm gonna use that water. So I'll go ahead and bring that water back in. And it's totally fine if you do this, where you just bring the molecules back in whenever you want instead of writing them along the whole way. When you're doing your mechanisms, if you find that you get to this point and you're like, I don't know what else is in solution, then it might be worth the time to keep writing it every time. Write that HSO4 minus each time. Write the water and HSO4 minus each time. So that way when you get here, you know everything you have in solution is written in the step with you, right? So that you get here and you're like, all right, cool. I have H2SO4, or I have H2O and HSO4 minus, and then I'm like, all right, so then the best base is gonna be that H2O. So that's what I'm gonna use. Again, remembering that this HSO4 minus, seeing the negative charge should signal base. I love negative charge does indicate base, but we gotta remember our exceptions. If you're the conjugate base of a strong acid, you are a terrible base. You're not gonna take things. Anything else will be a better base. So then, because we're doing acid-base, we again need to throw up those equilibrium arrows. So again, that would be the arrow that gets graded. We get our thiol, which again, I'm just gonna switch over to line diagrams because I don't feel like writing that in. I still need my inorganic product, which is that hydronium ion. So I would need to write all of it, right? Whatever was the base, you have to say that it took that proton. Oops, there we go. Okay. Now we're done. Now it looks like the product we need. Yeah. So you could use, no, you have to use water. So I was gonna say, if I don't tell you, and I just say use any reasonable base, then yes, you could use the thiol. Because it's solvent, as well as the nucleophile. The reason I know it's solvent as well is because I wasn't given anything else, and that is just like how alcohols can be both the nucleophiles and solvents, the thiols can as well, because sulfur acts like oxygen. So it would just be, this has to be the solvent, because that's the only thing over the arrow that is given to me. So you could use that again. But I'm gonna tell you right now, my instructions will actually say, use the best base in solution to try to limit you. so that then you would have to use water is what I would be looking for. Yeah. Cool. All right, any other questions about the mechanism? Yes. Yeah, so the reason why this alkyl shift happens is because we get a more stable molecule. We get a more stable ring. So even though the carbocation is less stable, we went from a tertiary to a secondary that normally would be a bad thing. But here it's okay, because even though the carbocation isn't more stable, the whole molecule is more stable, because that four-membered ring is really highly strained. The only thing more strained is a three-membered ring. So that four-membered ring is really highly strained. So releasing the ring strain is why we do the 4 to 5 expansion. And that would be an example of like a concept question that could be asked on the open-ended section, would be, I give you this, and I say this transformation occurred via an SM1 reaction. Why would that be favored? Rationalize that product formation. And so if you said increasing carbocation stability, that would be incorrect. The correct answer would be increasing ring stability, and that would be the answer, because we are making a more stable ring. That's the benefit there, is the whole molecule becomes more stable. Even though the carbocation's like a little bill, but the big payoff is the ring. So it's willing to like pay a little bit of energy towards the carbocation to have the whole molecule, the better of the molecule, be stable. Any other questions? Okay, cool. Ooh, look at the time. All right. Do we want to have class again on Wednesday like we did last time? Yeah? Okay, cool. It'll still just be review. We won't start anything new. It'll just be more review. It'll be the same deal as last time where it's just, optional. Okay, cool. All right. So looking at our study guide, our lecture numbers, again, were wrong here, and I don't remember what the right ones were. Let's see, what did I say? That sounds right, 16 to 31. I'm gonna trust you because I don't even see it right here. Yeah, there it is, yeah. I don't know why I said I was, yes, I believed you. 16 to 31. I just became like hyper fixated on trying to find it in the announcement, and I'm really sorry. When you said it, I should have just written it. Thank you. So yeah, 16 to 31 is, so basically today is the point. And actually, I guess we should say tomorrow. So I guess it should be 32. Wednesday. I think lecture 32 is Wednesday. It'll be everything up to the exam. That's the point. It's just everything. But have the warning that organic chemistry is inherently cumulative. So like how we talked about the stereochemistry of like, well, when do I use a wedge or a dash versus just lines? That was an exam 1 concept that is still very relevant. So like that's something that you still need to know. So here are some key topics that are still very relevant for the new material. So things we need to know are like our nomenclature and our common names and motifs and everything. So for the nomenclature, what I'll tell you is that there won't be like an explicit nomenclature question like there was on the exam 1 where I had like the 3 structures or where you have to go from name to structure, structure to name. But I might use a name in a problem, in which case then you need to know how to draw it to answer the problem, right? So you would still need to know nomenclature, being able to interpret it, but I'm not going to ask you an explicit question of like, name it, right? But you still need to know nomenclature for the exam. I hope that makes sense. Same thing with functional groups, especially when we're thinking about the functional group interconversions. We need to know our functional groups. Acid-base chemistry, absolutely. We've been using it a lot. The intermolecular forces and physical properties, thinking about like what could be a solvent in different boiling points and stuff. Newman projections. When were Newman projections really relevant? E2, right? So that's when we were using that a lot, was for that E2 discussion. How about stereochemistry? Like all of it, right? Yeah, like SN2. I heard SN2. We had it for SN2, we had it for E2, we had it for SN1 and E1. Because remember, for SN2, it was inversion. For E2, we needed it to be antiperiplanar. And so then that controlled our stereochemistry at times, right? Because you could get E or Z because it had to be antiperiplanar, right? So it could be E or Z, it could be trans or cis, right? But as long as it was antiperiplanar, because if it's not antiperiplanar, you are not doing E2. If it's not antiperiplanar, you can't do it, right? It must be antiperiplanar in order to happen. Then for SN1, what was the stereochemistry we saw there? Racemization. Every time you make a carbocation, you lose the wedges and dashes, right? Every time you make that double bond, you lose the wedges and dashes. So then if you're trying to show the racemization, you can either show it by drawing just the lines, not having wedges or dashes, or if you use a wedge and a dash, then you must show both. You must then show both the wedge and the dash, right? Because then you have to show both stereochemistry were created. All right? E1, what was the stereochemistry that we saw for E1? Either the trans or E, right? That was always our major. So we still need to know all of those stereochemistries because it was very relevant in our mechanisms that we were doing, right? And then even for oxidation and reduction, whenever you make a double bond, when you make that carbonyl, we again are going to lose the wedges and dashes because it's sp2. And then for the reduction, it again can happen on both sides. So I wrote racemize there, meaning that you get both the wedge and the dash. Right. Because the reduction is also going to go through where it can add to the front or the back. So that was the stereochemistry for the oxidation and reduction as well. Put a little box around that so we can see those as well. So those were the stereochemistries for those reactions. So then you still need to know, are we making a chiral molecule or an achiral molecule? Because that was, again, the chirality aspect of it. And then with our chair conformations, we need to be able to draw the chair flip still, and do the Newman projection of our chairs, and recognize the stabilizing and destabilizing factors of our chairs. So like the ring strain was one part of that, right? And then we also need to know like what was the, you want the large groups equatorial. So we had ring strain and large groups equatorial in order to make it more stable. So those are things we needed to know. And that became really relevant with our one quiz question. And actually, let me modify that quiz question. So I'm going to I want to illustrate something really fast in the last like 30 seconds. I'm going to make it generic. Let's do. All right, let's say you have this molecule, and you know what, I'm gonna even make it more complicated. I'm gonna add heat. So I have sodium methoxide and heat. Which mechanism am I going to go through? E2 is what our instinct tells us, right? But remember, our rings are locked conformations. So with that ring, you have to have the antiperiplanar. When I look at this, I want to do E2, but this is a wedge, I need the dashed hydrogen. The dashes are taken by R groups. I only have wedged hydrogens. So I want E2. Oh, change color. But there's no antiperiplanar. So then the product would have to be what? What's in competition with E2? SN2. So because E2 can't happen, my only option becomes SN2, where I would get that inversion. Okay, the last thing right before you leave, I just want to clarify this because I have been getting quite a few questions about it. For the topics that are going to be on the exam, this is everything that we discussed. I want to highlight the things that are not on the exam, especially looking at radicals. Anytime you see on past exams, because remember I changed when I added radicals in, I used to teach it at the beginning to follow the book order, and I've changed it to now put it at the end. So you'll see on some of my past exams, I use light. Anytime you see light, that is telling you radical. That means that we didn't do it. So that you can just skip that question on the previous exams because that's not something you will see. I don't expect you to be able to do that. So that was the big thing that I wanted to make sure you recognize when you're doing past exams. All right, for Wednesday, try to identify questions on, we'll do the summer exam probably, which ones on the summer practice exam that you want to go over in class. All right, have a wonderful day. I also have office hours both today and Wednesday. What's up?
Just one quick question.
Yeah.
When I was doing this at home, I got lazy with all of like the product solvents.
Yeah, that's beautiful. Yeah. So I was using different solvents to illustrate like different examples. Okay. But if you want to use the exact same aprotic solvent, cool.